Welcome to the High Voltage AI podcast. This deep dive is part of a special week-long series we're running in the High Voltage AI newsletter on Substack. We've designed this series specifically for electric utility engineers, looking at everything from overhead and underground construction types right through to the absolute cutting edge of energy tech. Today is Wednesday, and our focus is grid integration and industrial heat applications. This really gets to the core of how flexible nuclear operation and its potential for industrial heat, how it's profoundly reshaping electricity markets and process industries. It's actually fascinating to see power systems engineers right now designing grids around these small modular reactor capabilities.
And here's where it gets really transformative. It challenges, 70 years of assumptions about nuclear power? Pacific Gas and Electric, just this year, 2024, during their grid stability analysis for California's planned small modular reactor deployment, they found something remarkable.
Oh, what was that?
They discovered that small modular reactors can provide grid services that, frankly, traditional nuclear plants just never could, never designed for it.
That sounds like a huge shift, because traditional large reactors, they're basically baseload, right? Fixed output machines.
Yeah.
And we know that creates real headaches for grid stability, particularly as we get more renewables online. So what makes these small modular reactors so different? What's the core operational change?
It's a complete rethink of nuclear's role on the grid. Small modular reactors, they offer something like a 4-to-1 turn-down ratio.
4-to-1, meaning down to 25% power.
Exactly. They can easily scale down. And couple that with rapid ramp rates, 5 to 10% per minute.
Okay, that's fast.
It is. And critically, they can co-generate, produce electricity, and process heat simultaneously. So this operational flexibility, it positions them as a really crucial bridge technology. It helps integrate renewables, yes, but it also provides that high-temperature industrial heat we need for decarbonization.
So we're not just talking theory here. These capabilities are actually being built into projects.
Absolutely. The small modular reactor revolution in terms of power systems, it's already happening. Look at Utah Associated Municipal Power Systems, UAMPS. They've contracted for 462 megawatt electric of NUS-scale small modular reactors.
And specifically for what role?
Specifically for load following. And then you've got TerraPower's Natrium system. That one's unique. It integrates molten salt energy storage for, unprecedented grid flexibility.
Molten salt storage integrated right in.
Yes. So these aren't just papers or studies. These are real operational projects showing how small modular reactors provide grid services far beyond anything traditional baseload could dream of.
Okay, let's unpack that grid integration challenge more, because it's clear traditional nuclear just doesn't fit well with modern grid demands. What's the fundamental problem?
Well, our modern grids are facing this incredibly complex situation. You've got rapidly increasing renewables, fluctuating supply, and at the same time, industry needs both super reliable electricity and high temperature heat. Traditional nuclear, designed for steady, constant baseload, it actually makes these integration problems worse. It just wasn't built for the kind of dynamic balancing needed today.
And what are the specifics of that inflexibility? You mentioned fixed output.
Exactly. Large reactors, they run at 90, maybe 100% capacity, minimal load following capability, just can't really throttle down easily, and their response times, very slow. Ramp rates of only, say, 1 to 3% per minute. It's nowhere near fast enough for the kind of grid services needed now.
Like balancing solar variability second to second.
Precisely. And economically, their huge upfront capital costs mean they have to run constantly at high capacity to make financial sense. Even planning outages is cumbersome, 12 to 18 months. You're hitting a key point. Traditional nuclear offers minimal, almost no capability for automatic generation control that's essential for frequency regulation. Their reactive power capability for voltage support, limited compared to, say, a gas turbine.
Okay.
And a major practical hurdle. They can't restart grid systems without outside power. No black start capability.
That's a big deal in an emergency.
It is. And economically, running below rated capacity, they face big penalties. So load following is just not an attractive or often even feasible option.
We've seen this play out, haven't we? Like with Diablo Canyon in California.
Yeah.
How does its inflexibility show these challenges?
Diablo Canyon is a perfect example. It pushes out a fixed 2,200 megawatts pretty much constantly.
Regardless of demand.
Regardless of demand, regardless of how much solar is flooding the grid, it can't load follow during those high solar periods. This creates significant grid stability issues, especially during those times in California, with low demand but tons of renewable generation. That inflexibility is a key factor in why it's scheduled for retirement. It highlights the mismatch.
So it's really clear then. The move to grids dominated by renewables demands a totally different kind of resource. We need flexibility to compensate for variable generation, balancing solar and wind.
Yes.
We need super-fast, sub-second response for frequency events, ramping services maybe 10 to 20% per minute for load following,
Crucial.
and critically, that simultaneous electricity and process heat delivery for industry.
And this is exactly where small modular reactors come in. Their inherent design, their advanced controls, they allow for this variable operation safely and efficiently. They solve these integration challenges.
Let's talk numbers on that load-following performance. The source material mentioned some really impressive capabilities. How much can they actually adjust output?
They can operate across a surprisingly wide band, typically 25% up to 100% of rated power output.
Okay, that's a huge range.
It is. And they have those ramp rates we mentioned, 5 to 10% per minute for power changes, plus sub-minute response to automatic generation control signals from the grid operator.
Sub-minute. Wow.
And crucially, they're designed for daily load following, day in, day out, without degrading components. They're built for a 60-year design life with this kind of operation in mind. That durability is key.
And NuScale specifically, what are their load-following specs? Can you give us the hard numbers on that flexibility?
Sure. For NuScale modules, the power range is 19 to 77 megawatt electric per module. That's the 25 to 100% range. Their ramp rate is stated as 40% per hour, which is equivalent to 10% every 15 minutes. They achieve this using control rod positioning and also steam bypass systems. Very efficient.
And they tie into the grid control systems.
Yes, fully compatible with automatic generation control, ready to respond to the grid operator's signals automatically to balance supply and demand and keep frequency stable.
Okay, so beyond just following load up and down, how do small modular reactors help with more advanced grid services, like frequency regulation and voltage support?
Right, so for frequency regulation, they offer immediate governor response, that's primary frequency response, the instant reaction to a frequency drop, and they can participate fully in secondary response through automatic generation control.
How much adjustment can they provide there?
Typically a plus or minus 5% power adjustment capability specifically for frequency regulation, with sub-second response for that primary action and seconds for the secondary. Very fast.
And voltage support? Reactive power?
Robust capability there too. Plus or minus 40% of their rated power in reactive power. They operate with automatic voltage regulators, achieving a power factor from 0.85 leading to 0.95 lagging. That significantly boosts power quality and grid stability.
So they can actively manage voltage levels.
Exactly. Injecting or absorbing reactive power to keep voltage within the required limits. Vital for grid health.
Now, TerraPower's Natrium system adds that molten salt energy storage. How does that elevate its grid integration capabilities even further?
The Natrium storage is a really interesting addition. It integrates a 1,000 megawatt-hour molten salt storage system. This lets their 345 megawatt electric reactor push out a peak of up to 500 megawatt electric.
For how long?
For over 5.5 hours. And what's really impressive is the thermal storage itself. It boasts a 99% round-trip efficiency. That's incredibly efficient storage, a real game changer for stability.
Okay, so what specific grid services does that storage enable?
Well, it allows for significant peak shaving, delivering maximum power when demand is highest. It enables load smoothing, storing energy during low demand, releasing it during peaks.
Right, classic storage benefit.
Exactly, and that makes it fantastic for integrating renewables, smoothing out their variability. Plus, it opens up economic optimization through energy arbitrage, basically, storing cheap power and selling it when prices are high.
Small modular reactors also bring distributed generation benefits, right?
Yeah.
Helping with transmission.
Yes, huge benefits there. By generating power closer to where it's used, they drastically cut the need for long-distance transmission lines. This minimizes the strain on the transmission system during peak demand, reduces grid losses, and potentially defers or even eliminates the need for expensive transmission upgrades.
Puts generation closer to the load. Makes sense.
It does. Takes strain off the grid's backbone.
And what about grid resilience? How do these smaller distributed units make the whole system tougher?
They boost resilience in several ways. They have islanding capability. They can potentially keep serving local loads even if the wider grid goes down.
Okay.
They can provide black start service, helping restart grid sections without needing external power. And just having multiple smaller units instead of one giant plant distributes the risk. If one unit is offline, the impact is much smaller, more localized. It adds redundancy and operational flexibility.
Right, less reliance on a single point of failure.
Exactly.
Okay, let's shift to the power systems integration side. We've talked about the operational flexibility, which is amazing, but how does all that capability actually connect to the wider grid? What does this mean for the engineers doing the transmission planning, dealing with grid codes?
Yeah, integrating them successfully isn't just plug and play. It requires updated planning methods and a really solid grasp of modern grid codes to leverage that flexible operation properly. It's about optimizing the whole system.
So for transmission planning, what are the key things engineers need to consider when adding a small modular reactor?
You need detailed load flow analyses that model their load following accurately. You have to account for their ability to operate with both leading and lagging power factor. Calculating fault currents is critical for designing the protection systems, and dynamic modeling is needed to study transient stability, how the system reacts to sudden changes, all crucial for reliability.
And grid code compliance. The source mentioned FERC Order 841. What's that about, especially for something like natrium with its storage?
Right. Modern grid codes are increasingly demanding the kind of flexibility small modular reactors inherently provide. FERC Order 841, that's the Federal Energy Regulatory Commission rule. It's designed to help energy storage participate fairly in electricity markets. Under that order, the natrium system actually qualifies as an energy storage resource because of its integrated molten salt system.
Ah, okay, so it can play in more markets.
Exactly. It allows it to participate fully in energy, capacity, and ancillary service markets. And crucially, they meet the tough technical requirements, ramping, response time, voltage ride-through, frequency response needed to play in those markets.
What about protection system design? Integrating these assets must require some advanced coordination.
Oh, absolutely. It demands sophisticated protection schemes. Think differential protection for the generator, the transformer, the transmission lines, often needing high-speed communication between relays for proper coordination. And careful coordination with existing transmission protection is key, plus robust backup systems like distance and overcurrent protection. You need to detect and isolate faults instantly.
And grid synchronization, getting them connected and operating smoothly.
That involves several pieces. An interface with the grid operator's automatic generation control system for power management, capabilities for both primary and secondary frequency response, coordination with automatic voltage regulators for precise voltage control, and, of course, robust protection against under or over frequency and voltage conditions to keep the connection safe and stable.
Okay, let's talk economics, economic dispatch, and market integration. How do these small modular reactors actually make money while providing all these grid services?
Well, their flexibility is key here. They can actively participate in electricity markets in ways traditional nuclear just couldn't, optimizing their value across multiple revenue streams.
So what specific markets are we talking about?
They can sell energy in the day ahead and real-time markets, obviously. They can offer long-term capacity commitments. And they can sell ancillary services, frequency regulation, spinning reserve, voltage support. Plus, they can play in newer flexibility markets, specifically rewarding load following and ramping capability. It diversifies their income.
And the economics of operating flexibly like that, does it cost a lot to ramp up and down?
That's another advantage. They have very low incremental costs for load following. Ramping doesn't come with a big efficiency penalty like it might for some other technologies. So they benefit from those multiple revenue streams. They can optimize their overall capacity factor for maximum economic value. And they can be highly responsive to market prices, generate more when prices are high, maybe scaling back or producing heat when prices are low. It's a smart asset.
All right, let's pivot now to those advanced applications, specifically industrial heat integration. This seems genuinely transformative for decarbonizing industry. How do small modular reactors provide that high-temp heat while still making power?
They're designed to extract heat, often as steam, at various temperatures suitable for different industrial needs. Think low-grade heat, maybe 80 to 150 degrees Celsius, good for district heating, desalination, food processing.
Yeah.
Then medium grade, say 150 to 400 C, useful for chemical processing, oil refining, paper mills, and crucially, high grade heat, 400 up to maybe 950 degrees Celsius or even higher depending on the reactor design. That's the key for heavy hitters like steel production, cement, and hydrogen production. It unlocks decarbonization pathways that are really tough otherwise.
And NuScale specifically, what can they offer for industrial heat?
NuScale can deliver steam around 315 degrees Celsius at about 5.8 megapascal. That's quite high-pressure steam. They can provide up to 250 megawatt thermal of process heat per module, good for chemicals, refining, district heating, and a key point, they can often do this via dedicated steam extraction without reducing electricity generation. Dual output.
Nice. And TerraPower, how does their system fit with industrial processes?
TerraPower, with its higher operating temperature, can provide steam around 500 degrees Celsius. That opens up even more industrial processes. They're also targeting integration with high-temperature electrolysis for hydrogen production, direct process heat delivery, and using that molten salt system not just for grid power, but also for industrial heat storage and recovery. It's like a heat battery for industry, too.
That leads us right into hydrogen production. Nuclear integrated hydrogen could really change the game, maybe make green hydrogen cost-effective. How does high-temperature electrolysis work with small modular reactors?
Right. High-temperature electrolysis, or HTE, operates much hotter, 700 to 850 degrees Celsius. This significantly boosts efficiency compared to standard lower-temperature electrolysis. You still need electricity, maybe 4.5 to 5.0 kilowatt hours per kilogram of hydrogen, but you also add heat input directly from the reactor, around 1.0 to 1.5 kilowatt hour thermal per kilogram.
And that heat boosts the efficiency.
Dramatically. It gets the overall electrical to hydrogen efficiency up to 85, maybe even 95%. Using the reactor's heat reduces the amount of electricity needed.
So how does the small modular reactor integrate to optimize this?
The small modular reactor provides that essential high-temperature steam, usually from its secondary loop. It supplies the dedicated electrical power needed. And because the small modular reactor is flexible, you could potentially vary hydrogen production make more when electricity prices are low, for example, helping balance the grid. It all integrates with control systems for optimization, a flexible hydrogen factory, essentially.
And the economics.
Yeah.
How does nuclear hydrogen stack up cost-wise?
It looks very promising. Current natural gas reforming, the main way we make hydrogen now, is maybe $1.50 to $3 per kilogram, plus you often need to add carbon capture costs. Nuclear electrolysis today, using grid power, might be $2.50 to $4, but projected costs for small modular reactors providing dedicated heat and power, those could drop down to $1 to $2 per kilogram.
Wow. Potentially cheaper than fossil-based hydrogen.
Potentially, especially when you factor in carbon costs. And it's completely carbon-free. This targets a huge market, over $150 billion annually for hydrogen.
What about other big industries? Steel, chemicals. How does nuclear process heat help there?
Big potential. Take steel making, specifically direct reduced iron, or DRI. That process needs very high heat, 800 to over 1,000 degrees Celsius, and lots of energy, 11 to 12 gigajoules per ton of steel. Nuclear can provide that high-grade heat and the hydrogen needed as a reducing agent, potentially cutting carbon dioxide emissions by 95% compared to traditional coal-based methods.
Huge reduction.
Massive. And for chemical processing, think steam cracking for plastics precursors like ethylene needs 750 to 850 C. Ammonia synthesis, methanol production, refinery operations. Many processes can benefit from clean, reliable nuclear process heat and hydrogen supply.
So what are the big picture benefits for industry here? It sounds revolutionary.
It really could be. You get 24/7 reliability for process heat, which is critical for industry. You get high-grade heat perfectly matched to what the process needs. For the nuclear plant owner, you get multiple revenue streams selling electricity and process heat. And for everyone, massive decarbonization potential by eliminating fossil fuel burning for industrial heat.
Let's look at a real-world example. The Utah Associated Municipal Power Systems UAMPS NuScale project. This sounds like a prime case study for grid integration and load following in action. What are the project details?
Yes, the Carbon-Free Power Project, or CFPP as it's known, is a concrete example moving forward. The plan is for 462 megawatt electric total capacity. That's 6 of NuScale's 77 megawatt electric modules. It's being sited at the Idaho National Laboratory.
Okay.
And importantly, it's designed for both load following and baseload operation, connecting to the grid via 345 kilovolt transmission lines into the Western interconnection.
How is their grid integration strategy set up to meet the needs of all those municipal utilities involved?
The plan is for variable operation, specifically to match the collective demand profile of the member utilities. It's designed to complement their existing renewable generation sources. It will actively provide grid services like frequency regulation and voltage support, and its operation will be optimized through economic dispatch to minimize costs for the member utilities. It's built for their real-time needs.
What's the economic structure? How do the 46 participants share the costs and benefits?
It's structured with the participating municipal utilities and rural electric co-ops making fixed capacity payments, plus paying variable energy costs based on actual generation. This model offers them price stability, hedging against volatile natural gas prices, and they gain the value of the grid services provided. Commercial operation is targeted for the 2029 to 2030 timeframe. It's a collective bet on stable, clean power.
And the operational benefits for those members. What do they get out of this?
Well, their generation profile gets matched closely to their aggregated demand. They gain significant price stability compared to relying on fluctuating gas markets. They should see enhanced power quality and reliability on their systems. And of course, a major source of carbon-free electricity for their customers.
What about benefits for the broader grid, beyond just the direct members?
For the wider grid, a project like this provides needed transmission relief because the generation is more distributed. It enhances overall reliability by adding firm, dispatchable capacity. It adds flexible generation that complements intermittent renewables. And through economic dispatch, it helps provide competitive energy costs across the region it serves.
Okay, let's touch on some critical engineering considerations as we wrap up. Integrating small modular reactors clearly needs advanced protection and controls. What are the key technical standards?
Yes, compliance is key. IEE Standard 1547 is crucial that covers the interconnection requirements for distributed energy resources. It mandates things like voltage and frequency ride-through capability, participation in frequency response, strict limits on power quality issues like harmonic distortion and flicker, and anti-islanding protection. These are non-negotiable for safe grid connection.
And protection coordination. That's always a complex area for utility engineers.
Absolutely. It requires those sophisticated differential protection schemes we talked about for the generator, transformer lines, often needing that high-speed communication backup, plus careful coordination for bus protection to isolate faults on the station bus itself. It's about ensuring faults are cleared instantly and selectively, preventing wider outages. We're talking microsecond timing.
And the advanced control systems.
Yeah.
How do they mesh with grid operations?
It involves integration into the utility's SCADA system for monitoring and control, connection to energy management systems for automatic generation control, software for economic load dispatch optimization, and really fully integrated protection and control systems that work seamlessly together. It's about intelligent, automated operation.
For process integration engineering, especially delivering that industrial heat, what's involved there?
That's highly specialized. It means designing systems to handle potentially very hot, high-pressure steam, up to 500 degrees C, 10 megapascal. That requires robust, insulated piping, careful design for thermal expansion, pressure reduction stations, and efficient closed-loop condensate return systems, delivering the energy safely and efficiently to the industrial process.
And safety integration between the nuclear plant and the industrial facility must be paramount.
Absolutely critical. You need automatic isolation systems that can instantly cut off steam flow if the reactor trips, pressure relief systems like safety valves and rupture discs, coordinated emergency shutdown procedures for both the plant and the industrial process, and robust backup systems for any critical industrial processes that rely on that heat or power. Safety is job one.
And process control integration, making sure the reactor and the factory work together smoothly.
That involves integrating their respective distributed control systems, DCS, setting up automatic load shedding and restoration protocols if needed, continuous monitoring and control of steam quality to meet the precise industrial specs, and ongoing economic optimization of how heat and power are shared or prioritized. It's a complex balancing act.
So thinking about our listeners, especially engineers maybe looking at career paths, what kinds of opportunities are opening up in small modular reactor grid integration? This sounds like a really dynamic field.
It absolutely is. It's creating these really interesting specialized roles that blend traditional power systems engineering with this new wave of nuclear technology, a great frontier.
What about a specific role, like a grid integration engineer? What would they do?
Their focus would be on transmission planning studies for these new resources, designing the protection systems, ensuring grid code compliance. They'd need strong skills in power flow, stability analysis, protection coordination, using standard industry tools like PSSE, PSCAD, ETAP, PowerWorld. A professional engineer license is often preferred for that kind of responsibility.
And for market operations engineers, how does small modular reactor flexibility change things?
Their world gets more complex and interesting. They'd focus on the economic dispatch of these flexible assets, developing market bidding strategies, optimizing revenue across energy, capacity, and ancillary services. A background in economics, operations research, or power systems engineering would be key. There are clear growth paths there, from analyst roles up to managing operations or trading. It's about unlocking the financial value.
And on the industrial side, process integration engineers are key. What's the focus for a process heat engineer?
They'd be designing how the nuclear heat source connects to the industrial process, optimizing the heat balance, ensuring efficiency and safety. Skills in thermodynamics, process design, heat transfer analysis are vital. These roles are popping up in chemical companies, petrochemicals, steel, hydrogen developers. Usually requires a chemical or mechanical engineering degree with solid process experience.
And specifically for hydrogen, those hydrogen systems engineers.
Right. Their focus is integrating the electrolysis units, optimizing the whole hydrogen production process using nuclear heat and power. Need skills in electrochemistry, process control, system integration. It's a huge growth area with the expansion of the hydrogen economy, potentially a $50 billion plus market soon. Lots of potential there, from engineering to project management to business development.
So let's bring it all together. For all the power systems engineers listening, what's the real bottom line here? The key takeaways on small modular reactor grid integration and industrial heat.
I think the main point is that this convergence is happening now. Small modular reactors offer operational flexibility, load following, frequency regulation, voltage support that traditional nuclear just couldn't. This is absolutely critical for integrating renewables and keeping the grid stable.
And economically, it fundamentally changes the value proposition for nuclear power.
Absolutely. Those multiple revenue streams, electricity, capacity, ancillary services, and industrial heat, they create really compelling business cases. It makes small modular reactors a smart financial investment, not just an environmental one.
The potential for industrial transformation is huge, too, especially for those really tough sectors.
Yes, that high-temperature process heat enables decarbonization pathways for steel, chemicals, hydrogen sectors where electrification is difficult or very expensive. It opens up entirely new clean energy markets.
And it really positions nuclear as an enabler for grid modernization, doesn't it?
That's a great way to put it. Their capabilities fit perfectly with modern grid codes, market structures. They enable deeper renewable integration. They aren't just competing with it. They make the whole system work better.
And for careers, it's a new frontier, mixing disciplines.
Definitely. These specialized roles combining power systems, process engineering, and nuclear tech are emerging. It's a chance for engineers to grow their skills in a really critical field for the energy transition.
And crucially, this isn't just theory anymore. It's becoming market reality.
Exactly. Projects like UAMPS show this is moving from concept to commercial reality. We're talking operational plans coming online in the late 2020s. It's happening.
Tomorrow, Thursday, we'll shift focus slightly. We'll explore advanced materials, controls, and construction systems, really digging into how these innovations enable small modular reactor operation and are revolutionizing nuclear plant design itself.
That's the essential next piece. Today, we saw the market foundation, why grids and industry want these capabilities. Tomorrow, we look at the technological foundation, how advanced technology makes small modular reactor safety, efficiency, and flexibility possible.
So here's a thought for you, our listener, to consider today. What power systems or process engineering experience do you already have that might transfer well to these small modular reactor applications? Are you starting to see integration opportunities pop up at your utility or industrial company? Think about your experiences with grid modernization or process integration. How could they apply here? If you'd like to leave feedback or have any questions on today's deep dive, please feel free to reach out to our producer, Julius Quay, on LinkedIn.